Now, before we start band gap engineering, let us conclude our discussion on the defect, because there is another problem. You see that problem 2 is there, and why we are interested in problem 2, that we can compare the concentration of vacancy type of defects in metal as well as in a covalent crystal. So, we would like to compare this thing. So, let us take another example. This example is related to a covalent crystal germanium, GERMANIUM. The energy of vacancy formation in the germanium crystal is about 2.2 electron volt. Calculate the fractional concentration of vacancies in germanium at 938 degree centigrade, just below its melting temperature. What is the vacancy concentration given that the atomic mass and density of germanium are 72.64 gram per mole and 5.32 gram per centimeter cube respectively? Neglect the change in the density with temperature, which is small. So, here also like the previous example, you have to calculate the fractional concentration of vacancies at 938 degree centigrade, right, and then you have to calculate the actual vacancy concentration. Here you see the number of atoms is not given, rather atomic mass is given and density is given. Then you calculate, what should be the vacancy concentration in germanium, because for aluminum we have seen that it is how much, 1 into 10 to the power 19. Here you see what is the value for germanium. NV is given by n exponential minus EV by kT. First is the fractional concentration of vacancy, NV by n, it is equals to exponential minus EV by kT. Now, at 938 degree centigrade, that means plus 273 1211 Kelvin. So, at 1211 Kelvin, what is the fractional concentration? It will be exponential minus 2.2 electron volt multiplied by 1.6 into 10 to the power minus 19 joule per electron volt by K is 1.38 into 10 to the power minus 23 joule per Kelvin multiplied by 1211 Kelvin. And if you simplify it, you will get it is 7 into 10 to the power minus 10, okay, which is 7 into 10 to the power minus 10. What was the value for aluminum? It is no, at melting point it is 10 to the power minus 4, here it is 10 to the power minus 10. So, that means orders of magnitude less, minus 4 and minus 10. So, orders of magnitude less, not 1 or 2 or 3, not 4 or 5 times, 8 times, 10 times, it is orders of magnitude less in case of germanium. Now, what is the germanium, what is the number of germanium atoms in the crystal? How you can calculate? How you can calculate? You calculate. Yes, you calculate. 4 point? Yes, right. So, basically we have calculated the number of germanium atoms per unit volume it is given by n equals to rho Na y m atomic mass. What is the rho? Rho is 5.32 gram per centimeter cube, and what is Na? 6.02 into 10 to the power 23 per mole, and divided by m is 72.64 gram per mole. So, that means it is 4.4 into 10 to the power 22 centimeter cube inverse. Okay. Now, if you calculate the actual vacancy concentration in germanium near its melting point, so you have to calculate NV at 1211 Kelvin, that is equals to 4.4 into 10 to the power 22 centimeter cube inverse multiplied by how much? 7 into 10 to the power minus 10, and what is its value? Its value is 3.1 into 10 to the power 13 centimeter cube inverse. Okay. Now, if you take the ratio between the number of germanium atoms and the number of vacancy, what you find? That means 4.4 into 10 to the power 22 divided by 3.1 into 10 to the power 13. So, what you find? That is 1 in 10 to the power 9, 1 vacancy in 10 to the power 9 atom, 1 vacancy. In aluminum, what we find? 1 in 6000. So, which is high? Aluminum, obviously. It is mostly because of the thermal expansion at melting point at higher temperature. Metal expands more, covalent crystal expansion is less. Another important parameter is that you see how much energy was required to create a vacancy in case of aluminum. It is 0.7 electron volt, and here 2.2 electron, it is almost 3 times higher. So, that means creating a vacancy in covalent crystal is more and more energy is required, 3 times more energy has required in case of germanium if you compare with a metallic bonded crystal like aluminum. Okay. So, that is very important example to prove the point that a covalent crystal needs more energy to create a vacancy than a metal. Another application or of defect is the non-stoichiometry crystal. Say zinc oxide, let us take one example of zinc oxide. Let us take one example of zinc oxide. You see that here the red balls are oxygen and blue balls are zinc. So, zinc oxide, it is a stoichiometry zinc oxide crystal. It is perfectly all right, equal number of oxygen and equal number of zinc. That means, equal number of anion and equal number of cations are there in the crystal matrix. Now, if you find that there is some excess amount of zinc in the crystal, excess amount of zinc, how it happens? If the crystal has some deficiency in oxygen, suppose there are n number of zinc. So, how much number of oxygen must be there? N number of oxygen will be there, then only it will be a stoichiometric crystal. But if you have n number of zinc and n minus m number of oxygen, then it will there will be excess amount of zinc in the crystal. Now, when there will be an excess amount of zinc in the crystal, zinc is a cation. So, you see that this zinc cation is there in the interstitial position. You see this blue ball is a zinc cation which is in the interstitial position, and it has donated 2 free electrons in the crystal because zinc is +2, zinc is +2, that means it has excess 2 electrons when it is becoming a cation. On ionization, zinc has 2 electrons and zinc ion is there. That 2 electrons cannot be taken up by oxygen. Why? Because oxygen is in the form of anion. Since it is in the form of anion, it is not in a position to take up the electrons. So, you will have free electrons in the system. You see this zinc has given these 2 free electron, this zinc cation has given these 2 free electron, then there will be several zinc cations and multiplied by 2 will be the free electrons in the crystal. So, the crystal as a whole will be n type in nature, excess electrons will be there. So, it will be n type in nature. That is why as grown zinc oxide is always n type in nature. It is not intrinsic type, it is always n type. And during our discussion on the semiconductors, we have seen that some semiconducting crystals are p type in nature as grown. As grown means during preparation without addition of any kind of doping or impurity. Here we have not used any kind of doping or impurity, even then it is p type, it is n type in nature. Similarly, lead telluride PBT, it is p type in nature. Okay. See, it is because of the non stoichiometry, and it is a defect. Obviously, it is a defect that it is non stoichiometry. Because of the non stoichiometry, it is obviously the defect, and this has given you the advantage that without doping it is n type in nature. But how the crystal remains electrically neutral? How the crystal remains electrically neutral? So, basically you see that there are n numbers of oxygen cation and n number of zinc, sorry, oxygen anion and zinc cation, and 2 electrons are there for the excess zinc cation. That means, number of oxygen anion equals to number of zinc cation excess, say n number of zinc cation and 2 numbers of electrons for each zinc cation. That is why it is electrically neutral. Number of oxygen and number of zinc is same, and excess number of zinc is there. For each excess number of zinc cation, there are 2 electrons are there. So, that is why it is electrically neutral in nature. The crystal as a whole is electrically neutral, but it is n type in its conductivity because of the non stoichiometry. And this non stoichiometry is very important. In some cases, it has very important advantage, and it has some important disadvantage also. Now, what is the disadvantage? The advantage is that you get free electrons. Disadvantage is that you cannot, no, you cannot make it p type. It is very difficult to make it p type, because as you go on doping, it will be compensated by the electrons. Since there are many electrons in the system, it will be compensated by the electrons. If the number of oxygen is more than the zinc, then there will be anion type of defect, but that will not give rise to your n type conductivity. That will not give rise to n type conductivity. maybe it will be p type conductivity, but that is not thermodynamically favorable. So, it will never happen. In some cases it happens like lead telluride, but in zinc oxide you cannot grow p type using just excess amount of oxygen. That is not possible. Why it is not possible? The possibility is rare. It is because of this thing that zinc ion, its radius is zinc ion radius is 0.074 nanometer, right. Oxygen ion radius is 0.14 nanometer. Zinc atom radius is 0.133 nanometer. Okay. So, that means what will happen? Why I am citing this value? Yes, oxygen will never be able to occupy the interstitial position. Oxygen will never be able to occupy the interstitial position. So, that is why p type conductivity by adding excess oxygen is not thermodynamically favorable. So, there are constraints.
Again there will be cushion.
It is not a railway compartment. Okay, it is not a railway compartment. It has some thermodynamic consideration as well, and obviously it can push, but how far? How many oxygens will be there? Not many, because you see that it is 0.14 nanometer and it is 0.074 nanometer. So, only if there is excess zinc, the zinc ion can only be able to occupy the interstitial, even not the zinc atom. You see that the zinc atom, it is 0.133 nanometer, it is almost equal with the oxygen ion. Not even zinc atom will occupy the interstitial position. The interstitial position will be occupied by the zinc ion only. And when we talk about zinc ion, 2 excess electrons it is donating in the crystal lattice. So, that is why oxygen doping is not favorable. You cannot say that because of excess of oxygen it will be p type, not favorable because of the atomic dimension, because of the dimension. Okay. So, these are the two very important examples, say using which you can say that the defects sometimes give you some favorable advantage, and obviously we have seen that in case of say silicon. Obviously, silicon, the defect, intentional defect is nothing but the doping with the phosphorus or boron, it becomes n type or p type. So, that is also a defect. Sometimes in defect you see how the steel is prepared from iron, from normal iron. Yes. So, that is also a defect in the crystal. That is also a defect in the crystal. It increases the strength and other property many times. Okay, now we come to our next example of next topic of band gap engineering. This band gap engineering, you see that in some applications we have seen that a particular type of band gap value is required. We have talked about the fiber optic communication. There we have seen that 2 windows are there in fiber optic communication. Can you remember the value of the windows? One is 850, 1300, yes 1550, all in nanometer. When you talk about window, what is window basically? Window is nothing but where the loss is less, dispersion is less. Low loss, dispersion less fiber at these 3 wavelength of light, low loss, dispersion less condition can be achieved using these 3 sources of light. You know that for fiber optic communication, what happens actually? How the information is sent from one place to another place, how it is happened? It is by the total internal reflection of light. That means, ultimately you have to send light through the fiber, and you know that for any material the loss is a function of its wavelength, right. Say for silica glass fiber, fiber is made of different material. One is the silica glass fiber. For silica glass fiber, we have seen that at this true wavelength the loss is minimum. How the loss is measured? What is the unit of loss? What is the unit of loss? It is decibel per kilometer, and it is wavelength. We have seen that this type of a curve. That means, one is 850, this is 1300, this is 1550. That means, the loss is minimum. It is decibel per kilometer. Okay? And if you take these wavelengths, you cannot name any single material using which you can get such kind of emission. Emission means either you have to use a light emitting diode or a laser diode for sending the light through the fiber. Either you need a light emitting diode or a laser diode. And when we talk about the window, that means the emission from the light emitting diode or the laser diode must be either 850 or 1300 or 1550 nanometer. And remember that the present generation fiber optic communication, present generation does not use this 850. We use only 1300 and 1550 nanometer. Okay? Now, we have discussed many semiconductors, various kinds of semiconductors, and you know their band gaps. Some have narrow, some have wide, then silicon, germanium, indium phosphide, 3-5 semiconductors, 2-6 semiconductors, many types of semiconductors we have discussed. And you find that no semiconductor will be able to give you this kind of emission, because it depends on 1.24 by lambda. So, that means the band gap must be 1.24 by lambda in micron, then it will be in EV, Eg in EV. So, if you put this 1300 or 1550 here, you will get some value which is not available for any kind of semiconductors what we have discussed till date. Then what is the way out? The way out is that you have to grow new materials with this band gap. You have to grow new materials with this band gap. That is known as the band gap engineering. That is known as the band gap engineering, when 2 or 3 or 4 materials are mixed to form a new material to tune the band gap. That is the band gap engineering. Then there are some constraint also. One constraint is that these type of semiconductors are all epitaxial layers, because device is made out of epitaxial layers only. device cannot be made from bulk crystal. You will find that devices are always made of epitaxial crystals. That means some 1 micron, 2 micron, 3 micron single crystal layer. Then where those layers are grown? Those layers are grown on substrate. So, you need a substrate and there must be matching of the lattice constant between the substrate and the grown layer. That means, lattice matching must be there. Okay? So, that means, even if you can mix 3-4 semiconductors to form one semiconductor, but as you mix, say if you mix gallium arsenide with aluminum arsenide. Okay. So, what will happen? Galuminium, aluminum arsenide is formed, but care must be taken that that material must have the lattice constant same as that of the substrate on which you would like to grow the gallium aluminum arsenide. So, that is a constraint. You cannot use any kind of substrate for any kind of material. Okay. One constraint is that. Then another constraint is the growth parameter, that it must follow the phase diagram, because not all the materials can be mixed together to form a new material. It can be immiscible also. It depends on the thermodynamic phase diagram. So, that is another constraint, that you cannot mix chair with table. Is it possible? But you can mix water with sugar. Can you mix chair in water? Totally immiscible. So, that is also there. That means, those phase diagram constant is there. You see that one type of material can be AX B1 minus X C, AX B1 minus X C. If we take 3-5 semiconductor, then we can say that X atoms of element A and 1 minus X atoms of element B randomly mixed in the group 3 sublattice, and all the group 5 sublattice are occupied by element C. So, 3 elements are there A, B, C. And when we talk about sublattice means, say this is gallium, this is arsenic, this is gallium, this is arsenic, this is gallium, this is arsenic, then this is arsenic, this is gallium. Etc. So, that means you find that there are 2 sublattice, one sublattice is group 3, this one, that one, this one, that one, etc., and another is group 5 sublattice. And here in this example, you see that A and B are 3 group 3 elements. That means, X atoms of A and 1 minus X atoms are B are there in the group 3 sublattice, but all group 5 sublattice are occupied by element C. Then it is one material which can be formed by band gap engineering, and one example is aluminum gallium arsenide. You see that aluminum is also a group 3 element, gallium is also a group 3 element. If X number of aluminum atoms are there, then 1 minus X atom number of aluminum gallium atoms will be there, and those are basically from group 3 sublattice, and arsenic will occupy the group 5 sublattice. So, this is one example. Another can be A B minus B 1 minus X C X, that means, here A from group 3 of the periodic table and B and C are from group 5. So, that means, 2 elements from group 5 are from the which will occupy the sublattice of group 5 of both B and C. If X number of C atoms are there, then 1 minus X atoms of at a number of B atoms will be there. The example is gallium arsenide phosphide. Here you see that gallium occupies the group 3 sublattice and arsenic and phosphorus are group 5, they will occupy the group 5 sublattice. Okay. So, this is another example of the band gap engineered materials.
Sir,
Yes.
the active number of atoms.
Hmm?
There is the active number of atoms.
Yes.
If there are 2 atoms of phosphorus,
2 atoms of
1 minus X.
yes.
What is the meaning of atoms? So 1 minus X atoms.
No, obviously it is basically the mole fraction. It is basically the mole fraction. So, it must be say 0 to 1. That means, the value of x must be from 0 to 1. Okay. Let us take one example. Aluminium say 0.3, gallium 0.7 and arsenic. Okay. That means 30% of aluminium atom and 70% of gallium atom, then only there will be 100% of group 3 sublattice. Out of 100% group 3 sublattice, arsenic will occupy 30% positions and the remaining 70% positions will be occupied by gallium. So, that is the concept. Similarly, say gallium arsenide say 0.1, phosphorus 0.9. It means all the 100% position of group 3 sublattice will be occupied by gallium. 10% of the group 5 sublattice will be occupied by arsenic and the remaining 90% of the sublattice will be occupied by phosphorus. So, that is the thing. Okay. It can be other type of things, say it is quaternary, that means 4 elements are involved here, you see 4 elements are involved. 2 group 3 elements A and B and 2 group 5 elements C and D. So, they are randomly distributed and here you see that A and B from group 3 and C and D from group 5. So, indium gallium arsenide phosphide, okay, indium gallium arsenide phosphide, that means say indium 0.2, gallium 0.8, arsenic 0.3, phosphorus 0.7. Here you see that out of all the group 3 sites, 20% will be occupied by indium and remaining 80% will be occupied by gallium. Similarly, 30% of group 5 position will be occupied by arsenic and 70% of group 5, 70% of phosphorus will be 70% of group 5 positions will be occupied by phosphorus. Okay. Now, the implication of
So, can we mix the 135 and 126?
one,
For p-type doping, one element from second group.
it is not related to doping. Doping it is not related, it is basically because if you dope the material, the band gap does not change. I am talking about the band gap engineering where I want to make the new materials to tune the band gap for a particular application. Band gap does not change the during doping. If you dope silicon with p or n type, the band gap of silicon does not change. Similarly, if you dope say cadmium telluride or gallium arsenide or indium phosphide, band gap will not be changed. The number of electron or hole concentration will be different during doping. So, I am not talking about doping, it is not related to doping, it is related to band gap engineering where new materials are formed to tune the band gap for a particular application. Say for your fiber optic communication, you need 1300 nanometer or 1550 nanometer sources. So, you have to make new material with such composition, so that its band gap will be matched with.
But the thing is the same, if we are doping boron in silicon, then boron takes the sides of silicon. And same is the here, if I dope
Boron can be take the interstitial position.
Then after it goes to the vacancy.
No, no, it is the interstitial position as well. Do not mix up these two things. It is the regular lattice site. I am not talking about any vacancy or interstitial. If it takes up the interstitial or vacancy, not that it is occupying the group 3 or group 5 sublattice, because in silicon the whole crystal is neither 3 nor 5, it is the silicon crystal, and the boron is occupying either the vacancy position or the interstitial position. Here it is not the case. Here you have two sublattice, one is 3 and another is 5, and out of these two sublattice some engineering you are making, so that two types of elements will share the positions. It is not the vacancy positions or the interstitial positions, it is the regular lattice site position. I am not talking about any vacancy or interstitial. Band gap engineering is not occupation of vacancy or interstitial, is not related to the interstitial or vacancy. It is completely new material, and the whole crystal lattice or the crystal structure will be utilized, not the interstitial or the vacancy positions. So, do not mix up those two things.
Can we make the quaternary by using 1 second group, 1 third group, 1 fifth group and 1 sixth group?
You can do any kind of permutation combination, provided that it is miscible in nature. It is miscible in nature, and you can grow the crystal, otherwise theoretically you can do anything, but our ultimate aim is to grow the crystal for a particular application. It is not very easy thing, because you see that till today we have discussed this thing, till today blue light emitting diode or blue laser, material for blue laser or blue light emitting diode is not readily available. People use silicon carbide, people use nitride semiconductors. Yes, but it is not very easy. You cannot name any organization in India which can provide you with blue LED or blue laser, because nitride semiconductor growth is not very easy thing. Another thing is, because of the wide band gap, the doping is very difficult to make for any wide band gap semiconductors, because of the non-stoichiometry and the compensation of the dopant atoms. Theoretically you can make anything. Okay. So, now if you see those structures, you see that this is the constraint of the lattice mismatch. Here in the x axis I have shown you the lattice constant, and in the y axis the band gap. It is a plot. Now, say one example of growth of say indium, gallium, arsenide. Why I am talking about indium, gallium, arsenide? It is because it is a material for fiber optic sources for 1300 and 1550 nanometer. Okay. If you want to grow 1300 nanometer or 1550 nanometer fiber optic sources, then you have to use this material indium, gallium, arsenide or indium, gallium, arsenide, phosphide. These are two very important material. That means one this material gallium, indium, arsenide, phosphide, it is a quaternary, and one constant is that you have to grow in lattice matching substrate. What substrate? Say we have shown you 3 substrates, gallium arsenide, indium phosphide, gallium antimonide. Okay. These 3 substrates are shown you with the dotted line. That means gallium arsenide lattice constant is fixed, its lattice constant is fixed. So, this is the lattice constant for gallium arsenide, it is say 5.64 etcetera angstrom, this line. Throughout this line the lattice constant of gallium arsenide is constant. Similarly, indium phosphide lattice constant is 5. Not 87, it is 5.85. So, it 5.9, yes 5.87, right, 5.87 this line. So, now when we talk about indium gallium arsenide phosphide, you see that this is indium arsenide and where is gallium arsenide? It is gallium arsenide, it is phosphide, gallium phosphide. That means, indium gallium arsenide phosphide means it is a variation from indium arsenide to gallium phosphide, right. It is a variation from indium arsenide to gallium phosphide. Okay. Wide range of variation you can make. The band gap of gallium phosphide is 2.26, the band gap of indium arsenide is 0.47. So, from 0.47 to 2.26, huge variation theoretically is possible by changing the composition of X and Y. But what you find? You find that you can grow this material at two positions, at this position with some composition and at this position with some composition. Why? Because at 2 points only it is lattice matched to indium phosphide and gallium arsenide. That means, at this position you take this position, this position. This is the position for indium phosphide. Then indium gallium arsenide phosphide must be this thing, otherwise the lattice matching will not be there. At this point the lattice constant of the epitaxial layer will be same with the substrate. Similarly, at this point it will be same with the gallium arsenide lattice constant, because you cannot choose any material. Say you if you take this point, here also it is, you see that it is the position between indium arsenide and gallium phosphide, but why you cannot take this point? You cannot take this point because no substrate is available. So, that is a constraint that you have to choose proper substrate. Similarly, gallium indium gallium arsenide, you see that here also you can vary the indium arsenide to gallium arsenide. This is the gallium arsenide point, that means, if I draw, so it looks like this, it is indium arsenide point, it is gallium arsenide. Okay. You see that only at one composition it is lattice matched to gallium arsenide, this point, and that composition is gallium 0.47, indium 0.53 and arsenic. That means, only 47% gallium and 53% indium with arsenic, if you grow, its lattice constant will be same with that of the, sorry, it is indium phosphide, indium phosphide. Okay. So, different type of material you can grow, but problem is the perfect matching with the substrate, because normally in the market indium phosphide and gallium arsenide substrates are readily available. You have indium antimonide or gallium antimonide, but those are not very readily available. Let us take another example of aluminum gallium arsenide.
Here the gallium phosphide, this point extremen and indium antimony. For these two, no substrate is available.
Which one?
Gallium phosphide,
Gallium phosphide substrate is available.
but it's not matching with gallium arsenide.
Now, how it will match? Because the lattice constants are different, there is the vertical lines. Actually, if you take the gallium phosphide substrate, it will match with gallium phosphide only, or to some extent you see aluminum phosphide is very near. Okay. But if you use indium antimonide substrate, its lattice constant is very high, it is almost 6.5 or 6.6 type of thing. Here gallium phosphide it is 5.5 or even less than that. So, it is wide difference is there. Another example is very important example is the gallium arsenide and aluminum arsenide. If you take aluminum gallium arsenide, what you find? The lattice constant of gallium arsenide and aluminum arsenide is almost same. It is almost same. That means, you can grow any composition of gallium aluminum arsenide on gallium arsenide substrate, right? Agreed? Since the lattice constant of gallium arsenide and aluminum arsenide is same, so you can grow any composition of aluminum gallium arsenide on gallium arsenide substrate, because aluminum arsenide substrate is not available. Substrate is gallium arsenide, and since the lattice constant is very close, so you can grow theoretically any composition of aluminum gallium arsenide, that means aluminum X gallium 1 minus X arsenic. Theoretically you can grow, but there is one problem. The problem is this thing. This curve is plotted, in this curve we have plotted the band gap against the mole fraction of aluminum arsenide X. That means, this is gallium arsenide, this is aluminum arsenide. So, you see that at 0.45 it becomes indirect band gap semiconductor. Okay. So, aluminum gallium arsenide after 0.45 of concentration X, when X is 0.45, that means when aluminum is 0.45. So, up to 0.45 it is direct band gap. So, as you cross 0.45 it becomes indirect band gap semiconductor. So, what is the problem? Problem is that you can grow above 0.45, then it will not serve your purpose for light emitting diode or LED or laser, because yes, it becomes indirect band gap semiconductor, and you need the conservation of momentum. That means, some defect levels or trapping levels must be there, must be introduced. So, that is why this diagram will give you that you can grow theoretically, but this diagram sets you the limit that after 0.45 of aluminum, that means aluminum up to 0.45, gallium 0.55 arsenic, up to this composition it is direct, above this composition it is indirect. So, it is useless for you. Similarly, this is the example of say gallium arsenide phosphide. Gallium arsenide phosphide. You see that gallium arsenide here also up to 0.45 it is direct, then above 0.45 it becomes indirect band gap semiconductor. So, why is 0.45 means gallium arsenic is 0.55 and phosphorus is 0.45. Then it becomes indirect band gap semiconductor. So, when we talk about the band gap engineering, obviously it is basically the fabrication or the growth of a compound semiconductor on a particular substrate, but there the limitations are the substrate, and another limitation is the transition from the direct band gap to indirect band gap in many cases, not all the cases, but in many cases. And we find that for a particular atomic composition only it is lattice matched to either gallium phosphide or indium phosphide or gallium arsenide type of substrate. So, that is constant. And you see that these are the materials which are lattice matched to this substrate. That means, if you talk about indium gallium arsenide, it is lattice matched to indium phosphide. Then indium aluminum arsenide, it is lattice matched to indium phosphide. Gallium indium phosphide with this composition only, it is lattice matched to gallium arsenide. Aluminum indium phosphide, for this composition it is lattice matched to gallium arsenide. Then gallium indium arsenide phosphide is lattice matched to indium phosphide for y equals to 2.2x. Only for this value it is lattice matched to indium phosphide. So, that means you cannot grow any composition. Theoretically it is possible, but practically there is a limitation, and you find that on the parenthesis I have used the band gap, I have written the band gap, it is 0.74 electron volt. Then indium aluminum arsenide is 1.45 electron volt. Gallium indium phosphide with this composition is 1.96 electron volt. Aluminum indium phosphide with this composition, it is 2.45 electron volt. These are the band gap which will give you the different kinds of application. Okay. So, these are the substrate and these are the materials, right. Now, when how we will grow this material, how we will grow this material? This material can be grown, you see that using some epitaxial technique. Using some epitaxial technique only you can grow this material. Remember that you cannot grow this material using bulk crystal growth. Okay, bulk crystal growth is not possible for this material, because such kind of variation you cannot make. Not only variation, band gap engineering also incorporates the doping concentration, doping level of your choice. Say you need 10 to the power 15, or you need 1.7 into 10 to the power 18, or you need say 2.3 into 10 to the power 18. It is possible using an epitaxial growth technique. That kind of precise doping concentration and precise thickness is not possible in case of bulk crystal. It is an epitaxial growth technique, and epitaxy means a single crystal layer, very thin layer of some nanometers, some angstroms, 100 angstrom, 200 angstrom, 400 angstroms, right. So, how the epitaxial layers are grown? There are epitaxial techniques or epitaxial machines. One is known as the liquid phase epitaxy. Number 2 is vapor phase epitaxy. And number 3 is molecular beam epitaxy. Okay. These are the main 3 epitaxial techniques using which you can grow different kinds of materials for band gap engineering, right. Now, this vapor phase epitaxy is sometimes known as chemical vapor deposition or CVD. Vapor phase epitaxy is sometimes known as chemical vapor deposition, but chemical vapor deposition does not ensure that it will be a single crystal growth. It can be polycrystalline or amorphous type of growth also. So, that is why when we talk about epitaxy, that means it is surely it is a single crystal layer. Otherwise, VPE and CVD are the same meaning. The equipments are also almost same, and there are different kinds of CVD techniques using which you can grow different materials. So, in the next classes we shall discuss about the epitaxial growth techniques of material. What are the epitaxial growth techniques, how the material can be grown, how the machine look like, what are the advantages and disadvantages of different kinds of epitaxial growth techniques, what are the advantage of LPE liquid phase epitaxy over VPE, okay? What are the disadvantage of MBE over VPE, or advantage of MBE over VPE, those things we shall take care in our next round of discussion. But remember that this band gap engineering is very important so far as the electronic material, its processing and device application is concerned, because in some applications you will find that say solar cell. In solar cells, or we have discussed about say for sensors or say DVD or CD type of application, that means memory storage application, you need a particular wavelength of light, blue wavelength of light, then you need to make some band gap engineering, otherwise you cannot get that kind of a material. Not only is the material, its doping level, its thickness, its compositional purity, everything is involved in those materials. So, that in that sense the band gap engineering of material is very important advancement in case of electronic materials.